Alright, vertical tangent lines. To find the point where the function has a vertical tangent line, you're going to take the derivative and set the denominator equal to 0. So it's similar to a vertical asymptote. Essentially, it's kind of acting like a vertical asymptote for the derivative. If you want to find the actual point of that tangency where the derivative is equal to 0 in the denominator, you're going to solve for x. And then you're going to plug in that x coordinate back into the parent function. You have to be careful because not all x values yield a y value. If it doesn't, then we're just going to throw it out. If you want to write the equation of your tangent line, you're just going to go ahead and write x is equal to that x coordinate because remember all vertical lines have just an x-intercept, so x is equal to whatever your x value is. Number 1, find the points of any where the function has a vertical tangent line. Then we're going to write the equation of those tangent lines. So let's go ahead and simplify this. This is 3 minus x to the 1/3. So when I take the derivative of 3 is 0, so that goes away. Derivative of negative x to the 1/3 gives me negative 1/3 x to the negative 2/3, which is saying the same thing as negative 1/3 times 1 over the cube root of x squared. And so this is essentially negative 1 over 3 times the cube root of x squared. And I'm going to set the denominator equal to 0. And so if I set the denominator equal to 0, I can divide both sides by 3 and then cube both sides and then take the square root. But I think most of you guys can see that if I plug in 0 in the denominator, that's what's going to yield a 0. So in this case, my x coordinate that I'm looking for is x is equal to 0. That's what creates my point of tangency for a vertical tangent line. This is also the equation of the vertical tangent line, x is equal to 0. Now if I wanted to find the point, I have to plug in 0 into the parent function. So I know I have 0. If I plug in 0 into the parent function, I'm going to have 3 minus the cube root of 0. Well, the cube root of 0 is equal to 3. Alright, part B, let's go ahead and change the form. So this is going to be equal to parentheses 4 minus x squared to the 1/2. And we're going to take our derivative. So f prime of x is equal to, again, this is going to be chain rule, so derivative of my shell is 1/2 to the negative 1/2. And then my chocolate still stays the same, 4 minus x squared. And I'm going to take the derivative of my chocolate, derivative of 4 minus x squared is equal to negative 2x. And so if I was going to rewrite this guy, this is going to be equal to 1/2 times 2x over the square root of 4 minus x squared. And I think you can notice that if I can cancel these 2's. So this is equal to x over the square root of 4 minus x squared. And once again, I'm going to set the denominator equal to 0. So I have the square root of 4 minus x squared is equal to 0. If I square both sides, get rid of the square root, I get 4 minus x squared is still equal to 0. And then let's go ahead and move the x squared to the other side. So I have 4 is equal to x squared. If I take the square root, I'm going to get 4, plus or minus 2 is equal to x. And so those are my two tangent lines. So my first tangent line is x is equal to negative 2. My other tangent line, vertical tangent line, is x is equal to positive 2. And so I'm going to go ahead and plug these into my original function so I can find the actual coordinates. If I plug in negative 2, so the square root of 4 times negative 2 squared, well, that's going to be 4 minus 4, well, that's going to be equal to 0. So I have, again, negative 2 and then a 0. If I plug in 2, it'll be 4 minus 2 squared, which is 4 minus 4, so I have 2 comma 0 as well. Finally, the last one, consider the function defined by x times y squared minus x to the third, y is equal to 6. Find the x coordinate of each point on the curve where the tangent line is vertical. So we're going to use implicit differentiation to solve for our x. And so what that's going to look like is, let's go ahead and take the derivative of first. Derivative of x is 1 times my second, which is y squared, added to my first, times the derivative of my second, which is times 2y times dy dx. And I'm going to do the same for the second. The derivative of the second is going to be negative 3x squared y. And the derivative plus my first, negative y x to the third times the derivative of y is dy dx. And that's going to be equal to 0. And so I'm going to collect all my dy dx's and put them together. I have a dy dx here, I have a dy dx over here. And I'm going to move everything else to the other side. So I now have, I'm going to move my coefficient 2 in the front, so 2y, or 2x, y, dy dx, minus x to the third, dy dx, is equal to negative y squared, plus 3x squared, y. And I'm going to factor out my dy dx's. So I have dy dx times 2xy minus x to the third is equal to negative y squared plus 3xy. And then I'm going to divide 2xy minus x to the third. And I'm going to set that denominator equal to 0. And I hope you notice that I can factor out an x. So I'm going to do that. I'm going to factor out an x. So I have x times 2y minus x squared is equal to 0. So x can be 0, that's one of the coordinates, or I have 2y minus x squared is equal to 0, so I'm going to solve for x. So I have 2y is equal to x squared. And so our other vertical tangent lines, if I take the square root of both sides, are all the points where the square root of 2 times y. So those are our other points of where our tangent line is vertical. So all those coordinates.